Hey everyone, this is the C++ 101 class, week 4B. It's Friday the 4th of May, and I'll be here. My name is Nelson, and so will Gavin. Hey Gavin.
Hey!
Okay, so, yeah, I hope everybody's ready for a very interesting day today. We're going to be talking about functions.
We're going to be talking about obtaining a registration.
Yeah, I was going to say that, but then I realized, wait a sec, I still have 3 days to procrastinate. So, I don't even know why they make you register this.
Why procrastinate? That's not a good start. Why procrastinate now when you can do so tomorrow?
Yep. Okay, so I'm going to go ahead and toss up a simple program that hopefully everybody at this point will be familiar with. Okay, so what we're going to be talking about mainly in this class today are functions.
What's a function, Nelson?
Well, functions are really cool ways in many programming languages have a way to express a function, although they'll call them different things in different languages. So a lot of languages, they are called functions. In C#, however, you don't have functions, you have methods. Same with Java. And the difference being that those methods must be attached to an object. Now, functions are typically methods that are not attached to an object, and at the opposite end, functions are methods are typically. Which way am I going again? I can't remember. So basically,
functions can either be they can either be attached to an object or not.
Right, and if they are, they're called methods. And in a lot of languages, you'll hear people say method, method, method. And those are basically going to be the same things. But in C++ and in C, we can represent functions outside of classes, and that's what we're going to be talking about. Now, I do want to point out in some other languages that functions are called procedures or subroutines, and in some languages have both procedures and subroutines, and they both have different characteristics. But if you are familiar with a language that's like that, in C++, they're just called functions. Now, there still are methods in C++. Methods are, of course, member functions, but obviously that's out of the scope of what we're talking about right now. We'll get into more of that when we get into OOP. So, a function is basically a way to represent a block of code. And you'll see we have been using a function. This entire class, we've been using the int main function, which is a function in its own right, but it's a special function because defined by the specification, a function with the name main and an integer return type is considered to be the entry point into our program.
Anybody who's had the problem of, like I did first time out, coming from C# and capitalizing main will have found this out because it doesn't work anymore.
Yep. Functions are case sensitive, just like pretty much all of the language constructs of C++.
But over and above that, with main, it's looking specifically for a lowercase main.
Yes. And there's no alternative. I mean, of course, we could just...
define main.
But that would be stupid. Okay, so what we're going to do here is I'm just going to throw up some code. Or how about this?
Hello, world.
I'm going to throw up something more interesting. Okay, so we have a basic program here. Everybody should be familiar with this sort of logic. Now, for right now, what I'm going to show might not make sense in terms of the example is a little contrived, but just bear with me because this does lead into what we're going to be talking about. But let's say we wanted this functionality repeated multiple times in our application. Or furthermore, let's say we wanted to delineate this functionality in such a way that it isn't cluttering your main function. Now, creating additional functions, the first use that people will find for doing so before they start getting a handle on how to factor out certain expressions into functions, is they'll use them to break apart the main function. Because what we want to typically do is make our main function relatively straightforward. We want the main function to read like pseudocode, essentially. We want to invoke named pieces of code within main so that the logic of main becomes a more high level and easier to comprehend. And if you wanted to find the specific bits of the logic that goes inside those names, then you would navigate to the function definition. So if I wanted to turn this bit of code into a function, let's say for two reasons. Maybe I want to repeat this twice, and I don't want to have to copy and paste it. And maybe our main function is already so large that I want to name this block of code something that makes a lot more sense. So what I'm going to do is I'm going to take this code and I'm going to cut it. I'm going to go above main. Now this is very important. I have to go above main. I'll talk about that more in a second. And I'm going to type in the void keyword followed by an identifier. And this identifier is going to be the name of our function. There are two naming schemes that would be considered acceptable in my eyes and Gavin's as far as homework's concerned and as far as what you should be doing. Either use Pascal case or Camel casing for names. Now, I prefer Pascal casing because I am primarily a C# developer, or at least that's where the majority of the production code I've written has been in, and that's the very common naming style for C# and other languages like that. It's also a very common style in C++ in general, but I've seen maybe a 50-50 split between people naming their functions in Pascal case and Camel case.
But Nelson, I don't want to call my function Pascal.
Oh, right. Well, what I mean is the casing. So, for example, I'm going to call this function perform age operation. Then I'm going to open up a parenthesis and close a parenthesis. Then I'm going to open up a curly and close a curly. What I mean by Pascal and Camel casing is this is in Pascal case. We start with an uppercase, and then every other word is delineated by an uppercase as the first letter of the word. Camel casing would look like this. And again, it's been about a 50-50 split with C++. C++ has been around for a lot longer than other languages, and as a result, it's also been used in a lot more scenarios with a broad range of developers. So that's probably the reason there's kind of this schism in regards to naming. But again, I prefer Pascal case because I think that looks better. Now what I'm going to do is I'm going to dump the code I cut earlier into these curly braces. So you'll notice that our function here looks a whole lot like what main used to look like, except for we don't have the return 0 and we don't have this bit of logic. So now I'm going to type inside of main, I'm going to say perform age operation, then I'm going to open up a paren and close a paren and terminate. Now when I run this program, we will get the exact same behavior. So there's a few.
Do you want to go ahead and get people to write that out? We'll use it as a starting point for some examples of things and expand on it as we go. And just pause the video while you do that.
Yeah. Okay, so what we've done in effect is we've named a block of code and we've stuck it somewhere else. Now I want to point out that the order that functions appear in fact the order that everything appears in C++ is incredibly important. And we are actually going to be talking about the compilation process in depth. And I'm not going to, unlike Monday, I'm not going to say that till the end because it feels like that, talking about that earlier.
For the whole of the, yeah. Well, as Myriad just asked, just out of curiosity, does main always go to the bottom of the program?
No. But main, okay, so the order matters. If I define this function right here, main can use it. If I define the function below main,
show me.
Main cannot use it. And you'll notice we get a nice little compiler error saying perform age operation, identifier not found. Because someone was lazy
on the screen.
Yeah, it is right here. The C++ compiler looks line by line by line by line by line by line and never goes back. Now remember I said C++ compiler. There's actually three things that happen during compilation. There's the preprocessor compiler and then the linker. but the compiler goes line by line by line, and if he's not made aware of a function, he's not going to allow you to invoke that function.
Well, do you fancy, have you got the whiteboard there? You could give us a rundown of what does what in what order.
I want to get into return types and parameters first, and then
okay.
Get down.
Sorry.
Just going for my tie. Okay, so this function right here is currently just a named block of code. It's not really that interesting. It's just a named block of code. It doesn't really do anything special. The power...
Well, you wrote it.
Well, the power of functions is about functions being able to perform an operation and return a result, and to be able to be changed during your invocation. So, for example, let's say I wanted to have another function that asks you for your dog's age. So what I could do here is I could say perform dog age operation, and I can say enter the age of your dog, and I can say your dog is age years old, and which is, what is it, times 7 or times 14?
Yeah, 7.
7 years old in dog years. So now we can perform a dog operation. So that's kind of nice. But here's the thing. We can do better than this. You'll know the great thing about functions is to be able to identify a bit of logic that we can factor out into a function and reuse it in different scenarios. So you'll notice that there's a running theme with these two functions. And this would be even more apparent if these weren't even in functions. They would be more apparent if I just had this in main. You'll notice that if I dump this code back into main, that we have some very similar looking code. We can really do better to factor this out and make it cleaner. So what I'm going to do is I'm going to identify a commonality with this code. And the commonality that I see immediately off the top of my head are these 3 lines. And these 3 lines can be easily factored out into a function. But how do we write that function? Well, first of all, I'm going to give it the name getInt. So far, so good?
I guess that's going to get a number.
Yes. So we have some problems, though.
How do we get a number?
Enter your what? And then... So we have some blank spots here, because this type of function is not capable of handling what we want to express. The reason it isn't is because this method, this function, cannot be reused for multiple scenarios because we cannot alter the data that gets passed into the function.
Well, couldn't you just have different ones? You know, get your age, get dog age.
Yeah, I could have a get dog age, get your age function, but even then, we don't know yet how to pass that data back in. Like, how would I do this? I want to say int age, and then I want to say get int. How can we inform that we want to fill this variable with the result of this function? And how do we inform the function that we want to use a special prompt? The answer is with return values and parameters. So I'm going to go ahead and bring in string. And I'm going to give this a parameter to start off with. Actually, no, I'm going to do return functions first.
Mm-hmm.
So what I'm going to do is I'm going to change the return type of this function. Now, what you see here is the function's signature. We have the return type, we have the name, and we have the parameter list. So the first thing I'm going to do is I'm going to change the return type. This type that I'm going to use is going to be what type of value will get passed back to us by invoking this function. And then down here, I can use a very special keyword called return value. Now, the return keyword in the context of a void function does not accept a value. But if you have a function that it returns a value because it has a specified return type, the return keyword must be followed by an expression that is or can be convertible to the return type. So I return here temp, which is an expression. Now I could have said 100, that's also an expression. I could say temp plus 5, that's an expression as well. The point is that we need to say return and then a bit of code that will pass back data in the proper type. So now I can say this. I can say int myAge equals getInt, and now I can say int dogAge equals getInt. And I'm going to change these variable names around. Sweet. So now we can go ahead and run this program. It's going to say enter your question mark, okay. And then enter your question mark again, okay. So we do see here, and this is kind of formatted terribly.
It's Friday. It's New Line Day.
Yeah. So now you see that this data that I typed in happened to come in on line 9 in the getInt function when we asked cin to get input from the console. Then it was returned on line 10 and assigned to whatever we assigned the invocation of that function to. And we can see that we can prove that that works because you see that the dogAge and myAge variables are correct.
This isn't a question for Nelson, but more for people in the class, just because we've had some wrong answers to this before. But if Nelson was to comment out return temp line 10, you can go ahead and do that. But then don't do this. If he was to make the return type void again, what would come back from getInt? We've had some interesting answers there. We've had a lot of nada, nothing, nothing, zero, junk, a memory location, undefined, null, nothing, junk.
Oh, we got one right answer. No, two right answers.
We would get an error. It will not compile.
Yep. So when I type
well, actually, to be fair, I did say what would come back from that method rather than what would happen if you tried to run that program.
Yeah.
But still in all, we did get quite a few people saying zero and quite a few people saying junk. Do you want to go into that? What happens? What void really is?
Void really and truly is nothing. It isn't a value. It has no type. It is not a type. It is the absence of a type. And
it's the black in our paint pot. It's not zero. It's not the same thing as zero. It's not the same thing as null.
It's a concept that only exists on the compiler level. There's no data associated with void. There's no behavior associated with void. The only thing that happens with void is that it becomes an error to assign a method invocation that returns void to anything. Because, as you see, a value type of void cannot be used to initialize an entity of type int. And I just love the ridiculousness of that error message.
A value of type void
cannot be used to initialize an entity of type int. Gosh. I should have a long talk.
It is kind of on the level of you're being very silly.
Yeah, that's pretty much what it is. So void is, because C++ is a statically compiled or statically typed language, and it's a compiled language, we can't do this. Okay, so if I go ahead and add this back in, so int, you notice when I add an int, everything works. Well, it'll still not compile, but these two errors go away. Now when I try to compile, we'll get this nice little message, getInt must return a value. We are forcing that every single code path or execution of this function has to return a value. And we are guaranteed that by the compiler. So there's no way to return junk from a function. Okay, so we have
we solved one problem.
Yep. We solved one problem.
We know how to get something back from it, but how can we change its behavior without, adding another method in? Sorry, I'm going to be doing this a lot, I'm afraid, and probably Nelson will as well. Function. How can we do this without writing another function?
The answer to that are parameters. And parameters are a way for you to provide information.
Parameterize? Oh.
Parameters are a way for you to provide, which wasn't that much of a tongue twister, but for some reason it hit me. Parameters are a way for you to provide data into a function invocation. And that data depends not on how you define the function, but where you call it from. Because you'll notice that we want different behavior every time we invoke getInt. And what we want to change is we want the prompt to change. So let's go ahead and do this. I'm going to type in the word string, not strong, string prompt into these parentheses. And what I've done is I have now specified to C++ that it is only valid to invoke this function given that you pass in a string variable. Now, this variable looks a lot like our local variables, and it does look a lot like local variables, and it behaves very similarly to local variables. It's called a parameter. And what we have here is a type followed by an identifier. And the identifier will take the same casing as a local variable. So now that we have this variable, we can use it to whatever extent that we want to inside of the getInt function. So I can say, enter your prompt. So now I can use this, I am now allowed to use this bit of data everywhere that I can inside this function. But you'll notice now, you what?
If that was me, I would take the whole string in as a prompt, apart from perhaps the colon.
Yeah.
Well, certainly the word your.
Yeah, you're right.
I know.
Gavin. Okay.
But you can point out why, though.
Yeah, it makes it more flexible.
Because it's kind of key to the argument you're making.
Yeah, it makes it more flexible. So what we've done here is we've now specified that we must pass in a string bit of data. Now when I go to compile it, we'll get some nice errors. We get getInt. Function does not take 0 arguments. And
well, we know that.
Yes.
We just told it.
So you'll notice that the signature of this method has changed drastically since we started with it. It used to be void getInt empty parens. Now it's int getInt std string prompt. So now I can go ahead and pass in an expression that evaluates to a type that is compatible with the parameter. Which means I can type in a string literal here, because a string literal is assignable to an std string object. And I can say, enter your age. And then right here I can also pass in a string literal. I can say, enter your dog's age.
But wait, you appear to be repeating code.
Am I?
The strings that you're entering are very similar, serve a very similar purpose.
Yes.
And also, they're magic numbers, only they're not numbers.
Yes.
Okay, it's not going to work if you're not thinking in the same direction as me.
No.
The subtle prompt is, I was just looking at that going, I thought you could further work those through into...
Oh, well, I could as well have done something like string prompt prefix and say enter your, and then I could say prompt prefix plus age, and then prompt prefix plus dog's age. Although I typically wouldn't do this level of refactoring given 2 words.
No, that's true. Initially my thought was just in terms of having a prompt variable rather than a magic number, but I got rather overexcited.
But I have done stuff like this as well in the past. It depends on how much data is repeated. I wouldn't do it for 2 words, but I would do it for a more significant amount of words. And I also want to stress that, and this is a good example to stress the fact that what we pass in doesn't necessarily need to be a string literal or a string object. What we pass in must be an expression that evaluates into a string. And a string plus a string literal does evaluate into a string. So when I hit F5, we can enter my age and enter my dog's age.
Awesome.
And you'll notice enter your age and enter your dog's age. Okay, are there any questions about functions so far, at least about what we've covered? Because there's a lot of stuff that we have to talk about in regards to functions. We have to talk a little bit about stack frames, we have to talk about the linker, we have to talk about the preprocessor, we have to talk about header files, externs, and function prototypes. So are there any questions about what we've covered so far? Or is everybody doing good?
Questions need to go in the webinar question panel, by the way, for Nelson.
Yes, questions.
Putting is my catchphrase.
Okay. Can you pass multiple arguments into a function like a method in C#? Yes. We are not restricted to a single parameter. We can pass in as many parameters as we want. And I do want to
actually, I was just going to say, I've got a question in because I answered Chris's question in BuzzNet. I just want to check I gave him the right answer. Basically, methods are a subset of functions, yes? They are functions that are within a class or similar.
Yeah, they're just a name for member functions.
Member functions.
In C++,
the phrase.
you can call a function that's a member of a class a member function, but its better name is a method.
And the reason this is a thing with, I always say method because of C#, is in C# you can't have methods, you can't have functions outside of classes or similar. So consequently, every function is a method.
Yep, per definition, there's no way around it.
I just wanted to clarify that because Chris brought it up.
Yep.
And,
I do want to quickly point out some simple terminology. String prompt is a parameter. Okay, everybody with me?
Mm-hmm.
The expression that I placed within these parentheses are an argument. So, I mean, this isn't any thing that's mind-blowing. I just wanted to point that out. People get the word parameter and argument mixed up so much. I get the words parameter and argument mixed up when I'm talking fast, or been talking for a while. But it's important to realize that if somebody says parameter, they're talking about this bit. When they say argument, they're going to be talking about what you supply a parameter with. Okay, so let's talk a little bit about variable scope here. And we can talk about variable scope, and we can also talk a little bit about stack frames, actually. It might be easier for me to just go ahead and open up a whiteboard and actually talk about what stack frames are and how it relates to function invocations.
Cool.
Okay, so I'm going to go ahead and open up a new thingy thing and go into here, and then I'm going to go find my tablet because I had to move it off my desk to make room for my awesome Thai food.
Have you not got the official blue?
Official what?
The official blue. What's the hex value of the official blue?
Official blue? You mean like F or 0F0?
The blue board blue.
Blue board blue. Oh, that blue. I don't know what it is. And I have whiteboards. I don't have blue boards.
There's an official orange.
Well, yeah, but that's used for that's company colors.
Yeah. Sorry, my mind was wandering while Photoshop did its thing.
Okay, so
let's wave our hands.
Pretty much. I think Photoshop's brain broke. Okay, so what we have is what are called stack frames. So we've been talking about stack frames a lot. So basically, when our program starts,
Well, quick pop quiz while you're just warming up your handwriting. Who can tell me in one sentence the difference between stack and heap? Just in BuzzNet will do. Is pile a synonym for heap?
I've never heard anyone say pile.
Okay. We've got quite a few answers coming in. Are you looking at BuzzNet?
Yes.
I like Wick's answer.
Yeah. Okay, so what we have going on
put, sir.
here is I really want to talk quickly about the stack and the heap. No, I don't want to really. I'm not talking about the heap yet. But keep
you have to kind of talk about what the difference is.
I'll briefly mention it, but I really want to save that for the discussion about pointers because that's when the heap becomes important.
But just to point out what the stack is.
Right. So the stack is the bit of data that's provided to our program when a function gets invoked. So when main gets invoked, we get data available to us. We get our prompt prefix string, our string, then we get our int age, and then we get our int dog age. This is the stack frame of main. This is the data that's made available to us when the function main gets invoked. So an int is going to be 4 bytes, and the string is going to be, I can't remember what the string is. This is going to bother me. Give me a sec. I forgot.
That's disgraceful. Hand in your
32
coder
bytes.
card.
A string is 32 bytes. This allocation is not done during compile time. It's done during runtime. Basically what happens is the main function will count all of the local variables that it has and how much data it needs to hold those variables. So in this case, we'll get 4 plus 4 plus 32. So 4 plus 4 plus 32 is going to be 40. So main requires 40 bytes of information. That means the computer is going to allocate at least 40 bytes. Now, there's a variety of there is something called the return address that's popped onto the stack frame, and possibly other values to make it align with cache lines. But think of it like this: that main gets at least 40 bytes, and this string and these ints get assigned a particular bit of reserved memory when main gets invoked. So
and this is at runtime.
This is at runtime. The compiler informs or compiles in the program how much data the function needs to execute. And then at runtime, that data gets allocated. So online, you'll notice online, so this is main. When we get to line 18, we invoke the getInt method. So we jump into getInt. When getInt gets invoked, what happens is at least, remember at least, there's more to this than what I'm showing, but at the very least, getInt has a single int local variable, which is 4 bytes, which means getInt will allocate at least 4 bytes of memory onto the stack. This will get pushed onto the stack. The stack will look like this. It'll look like main, and then underneath main we have a string. I'm just going to end up repeating what I have over there, aren't I? Int, and then we have get int gets popped on, and then or pushed on, sorry, and then we have an int. So here's what the stack looks like right now when we're inside getInt. Now, is everybody with me so far?
Would this all be contiguous memory?
The stack will be generally, yes. Yes, it has to be. Or it doesn't have. I mean, it doesn't have to be, but it's typically going to be.
We'll getInt follow main at the next
on the stack, yeah.
Available memory location.
That would be the most effective way to do this. Although not necessarily true. Again, if the runtime wants to put in padding for some purpose to work with the CPU cache in some more optimal way, there's a chance that there'll be a padding between these two, but that's irrelevant.
But in general, normally, just the basic terms it is.
Okay, so is everybody following me so far?
Mm-hmm.
This is what the stack looks like when we invoke getInt on line 18. Now, when we enter getInt, we start on line 7, and we have access now to this local variable, int. We now have access to that local variable. It's in scope. It's accessible. However, on line 10, when we hit the return keyword, here's what happens.
Bye-bye.
So what happens is getInt gets popped off the stack. The memory's still there. It's probably assigned to still whatever temp was assigned to, but it's going to be overwritten the next time we invoke a function.
And there's no way of getting at it.
Yeah.
As far as the program's concerned, it doesn't know about it. Well, that doesn't exist anymore.
Yep. So when we hit return on line 10, and our execution jumps back into main. So for example, if I set a breakpoint here, and where's my step into? So if oh, great.
Is this going to send you into?
There we go. I got it. So if I step into getInt, notice my call stack right here. My call stack says getInt, and then main. This is the stack right now, which is represented in this Photoshop file.
And on the call stack in Visual Studio, it's obviously sorted the opposite direction.
Right.
The most recent is on the top.
But here's what it looks like in memory right now. Main has a string and 2 in scope. getInt has a single int in scope. However, watch the call stack closely. When I continue and hit, well, I have to provide something to see in. When I hit this return statement and hit F10, and then F10 again, you'll notice that that function got popped off the stack, meaning that this memory got removed.
Is everyone following so far? Because really, that is hard. That just happens over and again at different levels of amounts of things, sort of different hierarchical levels.
Right.
You know, main call in this case called getInt, but getInt might have called some form of input validation method that would then have been added onto the stack afterwards, and then they get unwound as they're finished with.
getInt actually loads up 2 different functions that could potentially invoke millions of functions inside of them. And as they return, so here, let's do this. So getInt will jump into the cout. Oh, and I can't believe you didn't mention this to me, Gavin. I mean, I know I failed, but come on, you gotta have my back. getInt.
If you tell me what I didn't know.
getInt has a string prompt, which is also pushed onto the stack.
To be honest, I had not the vaguest idea what you've written down there.
Here?
Because your handwriting is so truly appalling. Well, hey, I need to defend myself. That was the first thing that came to mind. Yeah, I can read it. I just chose not to.
Okay, so the getInt stack frame includes the local variables and parameters.
No one pointed it out. No one else pointed it out. None of them are paying attention. They're all drinking because it's Friday night. Debugger. Sorry, continue. C in and C out you were talking about.
Okay, so then getInt will push on another stack frame when it invokes the C out
At line
overload
8,
on line 8. And then C out will return, popping off it from the call stack. And then getInt will invoke C in. C in will return. And then getInt will return into main. So all of this stack data. Oh, wow.
Yay for shift.
All of this stack data gets allocated and deallocated at runtime, although it still is technically stack data. So it is, in a way, dynamically allocating memory, but not in the way that you would do so to dynamically allocate memory. It's not useful to think of this like dynamically allocated memory, unless you're doing fun stuff like recursion. So what's going on here is this data gets pushed onto the stack and then removed from the stack by the time main gets to line 19. So by the time main gets to line 19, that happens. And yeah. And then
a line.
Yeah, and then the next line is going to go ahead and invoke cout
do the exact
and
same
stuff.
thing.
But then it's going to eventually invoke getInt again. Which means 36 bytes of fresh new memory gets made available to getInt. So, how does everybody feel about this?
Yeah, as Atomizer pointed out, this is why the buffer overflows stuff before can overwrite the stack.
Yep. Where do we see the stack? That's going to be in the... you can see a visual representation of the call stack with the debugger, the call stack window.
I can't remember if I've asked in this class. Is it the same as the C#? You can only get at that when you're debugging.
Yeah, when you're debugging, you can go up to Debug, Windows, and then Call Stack, or Alt-7.
How does the program know how much space to reserve for the stack, since you could call an unlimitedly deep hierarchy of functions? Well, I think basically what Nelson did to put those, if you're back in code, that getInt method together, if you essentially unravel that backwards, you end up with the way the compiled program, or a better, what am I trying to say? You know what I'm trying to say, Nelson.
I don't know.
If you inline the method.
If I inline? Oh, well, yeah, if I copied and pasted this entire method into main. Is that what you suggested?
Yeah, basically. What the compiler does, where it basically turns it all back into linear code.
Yeah. So, okay, so then we get, how does the program know how much? Yeah, basically, but in addition, sometimes that isn't necessarily possible because we might be invoking a function inside of, we might recursively be invoking a function for an unlimited amount of times. Now, here's what happens, is the program knows per function how much memory to allocate per function. Generally speaking, now this isn't a requirement, but generally speaking, the stack frame is made available to your program in its entirety or in its maximum capacity when your program starts. I do have read stuff about the Windows kernel being able to have stacks split across different contiguous blocks of virtual memory. But typically, it's useful just to think of it like a contiguous block of memory that's made available to you when your program starts, which gets into the dreaded Stack Overflow. So what do people think is going to happen when I invoke this function?
It'll open up a browser and take you to...
Error, good, but we get some infinite loops.
We got a broken record explodes.
What we get...
Nothing you need to call it. Excellent.
Oh, well, I just called it in main. What I get is a Stack Overflow. This is the runtime. This isn't a compiler error. This is a runtime error, informing me that I have pushed so many things onto the call stack that there is no more room to push more things on it. And it'll throw a Stack Overflow.
And if you look at the call stack...
Yeah, if we look at the call stack, it's pretty massive. Like, incredibly massive. Yeah, it's going to continuously invoke itself until it runs out of memory on the stack.
Which is basically why you shouldn't ever do that.
Yeah. Well, which is why every example of recursion should always have a termination.
Yeah.
So that's what happens here. Is we continuously push on another thing, and that's me drawing with a mouse, by the way, which looks horrible. Basically what happens is we run out of memory off the stack. What were you saying, Kevin?
Well, this leads nicely to what Alan asked, which is, since getInt is getting pushed onto the stack, aren't we increasing the memory size by essentially storing an extra 36 bytes? Once that function pops off the stack, does that memory get removed?
No. Generally speaking, the call stack is nothing more than it's more efficient to have the call stack be stored in a contiguous block of memory, because that way you can simply have to have a number that represents the top of the stack, and then when you push on a new function onto the stack, you just increment that number, saying that the top of the stack is further up. And then when the function returns and gets popped off the stack, then your stack pointer gets decremented. So as a result, you aren't actually really allocating more memory dynamically, although it looks like you are. Typically, the actual implementation, and there's no steadfast rule that this has to be the implementation that an operating system uses. It's just generally always the case. You have a block of memory reserved for your stack frames, and that block of memory gets reused for stack frames as your program executes.
So how do we know the total amount of memory contained by the stack?
I'm not aware of the limit, and that's going to be processor dependent, operating system dependent, operating system version dependent, compiler dependent. The amount of variables that you need to...
How much memory is being used on the stack, I think, was what the question is.
There's no way to know. You would have to tap into a register on your CPU to find that. I'm fairly certain that that the current stack pointer is pushed somewhere on a register on your CPU. Can we see the limit in the debugger? Not to my knowledge. I've never tried, and I highly doubt it.
But hey, it sounds fun, so...
I highly doubt it. I'll take a cursory glance around, but I just highly doubt that this information is going to be presented to us, because it's not particularly useful. Yeah.
So, anything else on the stack, or what we've covered so far on the stack? Any more questions?
Well, I really want to quickly point out one quick thing. This is why scoping is so... Basically, I wanted to talk about the stack again, because I know a lot of people here, because they're in a C++ class, they're really wanting to learn this stuff. But in addition, that's why it's impossible for us to access local variables inside of another function from within another function. Because of the way stack frames work, and because it provides us a bit of scoping. Now, there are semantic reasons why we can't access this variable, Because whenever you see an open curly brace, you know that we've opened up a new scope. But there's also technical, or not obvious, but technical and understandable reasons why doing so would be impossible. And that has to do with how the stack works. So yeah, anyway, are there any more questions about this? So isn't using the function wasteful since we're using 36 bytes to pass to main function when we just reinitialize them? To be honest, the compiler probably inlines this function. I say probably because I don't know for sure.
See, that's what I was getting at earlier in terms of...
if I turn on optimizations, there's a chance that the compiler will literally inline that method. Inline means it takes this function and literally copies and pastes it everywhere it's used. However, here's the thing. Now you might say, first of all, oh, we're just wasting 36 bytes. I want to point out that allocating a stack frame is ridiculously, stupidly, insanely cheap. And that amount of allocation and the nanoseconds that it might cause as far as performance, if that, are completely irrelevant to your code actually being written in a way that is understandable. Furthermore, if we had invoked this getInt function in 200 times during this program, it actually is more efficient to load it in as a function because the size of your executable also has performance implications. And of course, inlining a function is going to increase the size of your executable. So it's not important, basically, is what I'm saying. You're not going to in any way notice this code impacting the memory of your or performance of your program.
This might be slightly too esoteric, but if it were to inline getInt into that, would it still have the temp variable and so forth?
Probably not. That's optimization. That's optimization.
Sorry?
What?
Sorry, lag.
That's optimization compiler dependent. I'm not 100% aware of all of the optimizations that the Visual C++ compiler performs on a release build. And furthermore, the optimizations that it makes are dependent very, very specifically on metrics that are more or less a black box to us lowly developers. So...
So... stack. How do we make variables globally available?
We'll be talking about that, but I'll give you a sneak peek.
Like that. Right. Now, what's next on the... I think you should give them something to do.
I think I should go outside.
You should give them something to do, and then...
I always feel bad when I do that. I like being here when they're doing stuff, because then they don't get a break.
Well, I'm here.
Well...
Oh, I see what you mean.
Yeah. I say we go...
Well, we can run it into break anyway, because it makes it easier with the recording. We have to stop once.
Well, I'm going to go ahead and pause. Okay, I just resumed temporarily to ask that everybody, and I'm going to go ahead and reset your ready buttons, goes ahead and writes me...
Because, hang on, just to answer Bando's question about, we snuck the bubble sort in on them, because you didn't have to use recursion for the bubble sort.
Right. Recursion is one of those things that is non-obvious to people, but it's obvious to people who've used it, which is actually, you can describe programming like that entirely.
And not only that, here's an even better way to answer the question, because this is something that you guys are going to be asked to do in a matter of minutes. For the bubble sort, you guys had a whole week on that.
Right.
This is true.
So yeah, so go ahead and write me a getString method that follows this same sort of scheme, accepts a prompt, and returns a string. And we're so resuming. So the way that people should have coded this out is like this. So it's a getString method that just follows the same sort of pattern that we had before. Very straightforward. Okay, so are there any questions about functions? Any more questions about functions? We've talked about what functions are, the syntax, parameters. We've talked about variable scope. We've talked about stack frames. We've talked about calling functions. We've talked about return values.
Overloading?
I was going to get to that next, actually.
Cool.
Okay, so let's talk about overloading. There. Talked about overloading.
That was pretty easy.
Okay, function overloading works similarly to function overloading in a variety of other statically typed languages. What it is what we can do is we can define multiple functions with the same name, but with a different parameter list, and optionally a different return type as well. One of the more common scenarios for function prototype or overloading is providing default values for functions. So what we have here is we have a getInt function and we have another getInt function. Now, I want to point out, though, that the order does matter. The C++ compiler looks at things line by line, meaning we must define the getInt overload that accepts a string before we define the overload that does not. So what happens is the C++ compiler will examine your parameter list or your argument list that you pass into the function on invocation, and it'll identify the best suited overload to actually invoke, and it'll invoke it. So for example, if I were to remove my arguments from line 22 and run this program, it'll now compile because our zero argument method getInt gets invoked. And as you see, we get a prompt saying enter a number. Okay, so some rules. Overloading cannot be, function overloads cannot differ by return type. Solely. Now, if you can have two overloads with different return types, but you cannot differ solely from return type. So, for example, I cannot write a float getInt method. Not only would that be stupid semantically, but it would also be invalid because we are now not differentiating these two functions based off of our parameter list, because the parameter list is the only thing it looks at, and these are the same. However, we can do this. Because we've differed in our parameter list, we were allowed to do the overload. And because we were allowed to do the overload, we were allowed to supply a different return type.
Cool.
So, a few other interesting things about function overloading. So, for example, if I go ahead and add a 10 and a 10.0, what do you think is going to happen? Anybody have any ideas about what's going to happen? Looks like we got some C++ people here, or C# people in the crowd. Wow. Well, we got one person who's got it right. You'll notice the squigglies. This is an error. Unlike certain languages, when C++ cannot find a suitable overload, it will freak out. When there is overloading involved, it will throw an error because it doesn't have the same sort of logic to identify the most appropriate overload. If, for example, I were to remove the double add method, notice this compiles. Yeah, this compiles. 10.0, or maybe a better example would be 10.5, simply gets truncated when it gets converted into an integer. However, again, this does not compile, because now we've confused the compiler. It doesn't have any logic in the specification that provides a better match. So what can we do? Well, we can do one of two things. We can either forcibly cast 10.5 into an integer, in which case we will be invoking the int overload, or we could forcibly cast our int parameter, or int argument, into a double, in which case we'll get the double overload.
If you were to forcibly cast it into an int, just out of interest, and probably to remind most people, what would the actual result of that add be?
20.
20.
Yep.
Right, yes. Because it's truncating it,
yep,
not rounding it.
Yep. So what about this? You'll notice that when I specify a float and double, this compiles and uses the double overload.
Presumably that's because well, a float is still more precise than an int.
Yeah,
so it can't use the int.
Right, by doing this, we've ruled out the int completely, and so now there's only one left. But, just to confuse everybody even more, what happens when I add this function? And I'm not going to complete it. In fact, I'm just going to leave it commented out. When I uncomment this, what will the result of line 35 be? Notice we're passing in a float and a double. The answer is, we get a nice little error. Because now we've thoroughly confused the compiler again. Now it says, wait a sec, I can stuff a float in a float, and I can stuff a double in a float or a double, but I don't know which one and then it just dies. And says, can't do this. So there are some very interesting, non-obvious, and I mean just things that you have to keep in mind, rules about function overloading in C++. Are there any questions about function overloading?
Yeah, I was going to say, would your approach be to, say you had to have various different types of method like this, would it be to simply have the method do everything at the double level and then cast outside of the method, cast on return?
I don't know what you mean.
So you say if x equals an int cast of add and then only have a double add.
Oh, no. I would go with this, and then I would just pass in similar parameters.
Because obviously you could end up with an astonishing array of different one int and one float and a double and a double and a...
Yeah, it gets more complicated when we actually start talking about real-world examples, because right now this isn't really a real-world example because, well, there's a better way to add things in C++, and that's with the addition operator. Okay. Can you have an auto return type or auto parameters? Answer is no. You cannot use auto as a return type or auto as parameters. I mean, that's just one of the rules. So I cannot say auto get int. You'll notice that this is going to result in an error, compiler error specifically.
It has no way of working out what that should be.
Yes. Although you could argue, well, the return type is going to be an integer, and the answer is they just didn't make implicit typing that intelligent. So,
You had a couple of questions come in about why would you want to overload?
One of the reasons is providing default arguments. Now, C++ does have default arguments, although we're not talking about those right now. But oftentimes, you might want to perform some operation. Let's say you have a default argument, but to get the default argument, you want to perform some sort of computation beforehand. In addition, well, I mean, that's going to be the biggest one. And the second biggest one is for math operations. Because with math operations, you'll want to provide overloads for a bunch of different types of parameters. And as well as functions that take in multiple things of different types. Now, we haven't talked about OOP yet, or not very much. We haven't talked about OOP. And we're not going to be creating our own types in this class until later. So, as a result, it's difficult to show an example where you would use it, because oftentimes something that you can do with overloading that you can't do with default parameters is with when you have a function that can accept two different types of variables or two different types of parameters, and then it knows how to operate on either one of those. So it gives you a little bit of flexibility in your caller code.
Cool. And yes, so somebody said, so just because a function has a return type, you don't have to use it?
At the call site, the answer is no. So for example, if I make this code compile again, this is completely valid. It's not even going to throw a warning. You aren't forced to do anything with the return type. Now remember, the return type of a method, a function invocation is an expression. This is an expression. And I've been saying the word expression a lot. Expressions are really important. When I say an expression goes here, I mean anything that is an expression, which includes function invocations. The ramifications of this is that a function invocation can be used inside of a function invocation as a argument, because an argument is an expression. And we can continuously do this.
But the key thing being, at this point, that is utterly useless, because we're not assigning the return to anything.
We're not assigning the ultimate return to anything, no. But I just wanted to point...
after line... Oh, sorry.
I just really wanted to point out that you can use the return type also in any where the expression is required. So we can even do this. We can say cout add get int LHS get int RHS. And then when I run this code, I can type in 10 and 3 and I get 13.
Cool.
What happens if I have different code in one of the add functions? Doesn't matter. I mean, I'm allowed to do this. Now when you call add on a float, you use Stack Overflow, and when you call add on a double, you get a console message, and then you get a subtraction operation instead. But you're perfectly allowed to do this. These functions are completely independent of each other. The only thing that relates them is the name. So would that function take up 8 bytes? It would take up at least 8 bytes. I want to stress this. Function stack frames are not necessarily going to be exactly how much it needs for the local parameters. In fact, it's never going to be, because there is additional overhead that's required for a function for a stack frame to be used, specifically the return address. In addition to that, the operating system gets to decide how much memory gets allocated for a stack frame. And it could use this to perform optimizations. So, for example, to minimize cache misses on the CPU. So it doesn't really matter. Well, it does matter. It's important to note that at least 8 bytes are being allocated for this, but it's not useful to think that only 8 bytes are being allocated for this, because that's up to the operating system.
In memory terms, if it's got a return type, is there some sort of just almost like an invisible
Yes.
variable that it returns into that is then assigned to the actual
right
back at the call site? I mean, if you were to actually use do whiteboard out like you did before, but for that add method in use.
Well, typically what it's gonna use though is a register on the CPU.
Right.
Although it doesn't have to. It's implementation specific. Okay, are there any questions about functions and function overloading? Because we're going to move right along to the most complex bit of this discussion. We're going to be talking about prototyping, header files, CPP files, the preprocessor, and the linker. Okay.
The linker returns.
Yes. I'm going to remove all these add methods. They're kind of getting in my way. Function prototyping. So we've established right now that if I were to move these functions out of order from main, main would no longer be able to access them. We would get a nice little compiler error every time that we try to access this function. What you can do in C++ is what's called function prototyping. And this becomes this is an incredibly important concept that doesn't seem all that amazing right now, because you're just going to say, well, why don't you just declare the functions above main? This leads into being able to separate our functions between files, which is very important. So a function prototype is essentially the signature of the function. Basically what I've just done is I've promised the compiler. Remember, we've already established that the compiler isn't that smart. It reads line by line by line. And on lines 5 and 6, I am promising the compiler that there is a function in my program somewhere called getInt that returns an integer and takes in a string. I also promise that there's another function called getInt that takes in nothing and returns an int.
And do those have to be in the same order as they are?
Nope. Function prototypes can be declared in any order. However, this function prototype must be defined before I include string, or after I include string. Because if I didn't include the string header, then this would be an error.
Mm-hmm.
Okay, this program now compiles. Which is nice. So by promising...
So Nelson...
What?
I'm just going to say, so Nelson, why don't you just move the method above main?
Well, first of all, the first thing is about the fact that organization is really important in coding, and having main at the top of your main.cpp is something that isn't always followed. Some people don't really care that much. I do. I like seeing the main function. I like being able to easily find the main function.
Makes sense.
But this gets into the linker, and it allows us to do some cool stuff with different files. I'm going to show one example of an error, and then I'm going to ask if anybody has questions. Then we'll move on to header and CPP files, because that's where stuff's going to get fun. So if I remove this getInt function, you'll notice I don't get a compiler error. The compiler was totally cool with that. I told the compiler that there is a method of this, and the compiler was like, oh, dude, so I'm going to go ahead and just pretend that you're right, and I'm going to allow you to compile all this code, and I'm going to just hand it off to the linker at the end, you know, because you promised me that these functions existed. And so I'm going to let you use them, but then I'm going to hand you to the linker to actually find them and match them up for me. So when I do a Control-Shift-B, you'll notice I don't get a compiler error. I get a nice little linker error. And linker errors are notoriously difficult to read. So what we get is unresolved external symbol, int __ c decal getInt class std basic string character struct std character, traits, character, class, std, allocator, character, get int, and then a bunch of stuff I'm not going to try to even say. This is known as name mangling, and that's literally what it's doing.
Something to do with an alligator.
Yeah. Well, what it is the reason we can have function overloads in C++ is because the C++ compiler actually mangles these names when it compiles. So it actually encodes the parameters into the name of the function that gets compiled. So that's how it can differentiate between the two. And that's why linker errors look like this. Because the linker only gets the mangled name. It doesn't get the unmangled name. Anyway, so that's very important to be able to know how to read linker errors. And saying unresolved external symbol, which is the most common linker error that you'll get. And then if you look really closely, you'll see right here, there's your function getInt. And then you'll see right here, referenced in function underscore main, which is what main compiles into. Main doesn't get mangled. Well, it does. And essentially, it gets an underscore, but that's the C thing.
So basically, what happens is the compiler says, "Yeah, that's fine," because you're telling me that getInt with exists. It's probably in another file.
Yep.
And then the linker says, "Well, I've looked in all the files. It ain't there."
Yep. So get used to reading linker errors because you'll see a lot of them. There's one more linker error that I want to show people. If I declare this function twice, actually, in this case, I'll get a compiler error because they're in the same file. If they were in different files, I would have got a linker error. So I'll get into multiple files. Okay. So is everybody good with function prototypes? We're basically promising the compiler that this function exists somewhere. Okay, so how can we take advantage of function prototypes? Well, like I said, like Gavin actually said, it doesn't matter which files these are defined in, meaning I can define them in any CPP file that I want, as long as it's part of the same project. So I'm going to go ahead and right-click on source files, go to add, and hit new item, select CPP file, and give it a name. I'm going to say input. I'm going to have an input.cpp file. And then I'm going to move our two getInt functions from main into input. And finally, in input, I'm going to include in string and say using namespace std. Now I can compile and run just like before. Derp. I need iostream too. So what I've done is inside of main, I promised the compiler that there would be a function named getInt with these parameters and this return type, and same with this function. And then I'd actually define them in another class. I want to point out this is very ridiculously, incredibly important, and if you don't commit this absolutely 100% to memory, then working with multiple files in C++ will be a nightmare. C++ typically will only compile CPP files, and it compiles them individually. Each one of these CPP files gets threaded into the compiler, and on an individual basis, meaning that the include iostream and the include string and the using namespace std, these are local to this one file, which means we have to redo it here. Very, very, very important.
Just like in other languages that are available with your usings.
Yeah.
A using in one CS file doesn't affect another CS file.
Right. And the same thing with includes here. So every other file is typically ignored in C++. .h files do not get compiled. .cpp files get compiled.
.h files?
Yes, .h files. Okay, I do need to come up with a better example for this first, though. Okay, so is everybody good with the fact that I split these definitions into their own CPP file? I declared them above here, and then I defined them over here. And if I were to take out these prototypes and try to do a build, I would get 2 errors. Compiler errors, specifically. Now, here's one thing that I wanted to show you. If I included 2 getInt implementations, one in main.cpp and one in input.cpp, now I'm not going to get a compiler error, because as far as the compiler is concerned, these are separate implementations. But then the linker goes to create my executable and says, hey, you defined a symbol twice. You defined this getInt method twice, or getInt function twice.
And we did have a question. Do all these files have to be in the same folder upon compiling, or can they be linked to multiple folder locations?
The locations are completely irrelevant. It just happens that I'm working in Visual C right now, and I'm using my Solution Explorer, which will result in the files being in the same folder. However, if I was invoking the C++ compiler from a command line, I could specify CPP files all over my hard drive if I wanted to. And we call these prototypes linkers. No, the prototypes are called prototypes. The linker is what works with the prototypes to produce the result that we want. And after we get into .h files, I'm going to jump into the whiteboard.
The linker's like Batman.
Like Batman?
Do you know, it was like Batman the other day. He loomed for the whole class in the shadows. Have you completely forgotten that we did this on Monday? You know what a computer is, right?
What's my name?
Rainbow Dash.
Oh, right. Is there an order that it reads the multiple files? There probably is, but it doesn't matter. There probably is, per the implementation of Visual C++, it might do it alphabetically. Maybe it probably does it. Basically, the Visual C++ compiler is a command line tool, and the Visual C++ IDE simply invokes that command line tool and specifies a project file for it to build. And I'm sure the order that it compiles these files are defined in some way, but the point is it doesn't matter. There's no way that the order of the files of your CPP files being compiled has any correlation or any important relevance to anything.
Marcel's question that just came in appeared in BuzzNet just now as well, which is how does main know about input.cpp? There's nothing to tell main that input exists.
There isn't. The compiler doesn't. The compiler has no idea if the compiler. We promised the compiler that these functions existed somewhere. The compiler just took our word for it. Then, after the compiler got done with this file, and then after the compiler got done with this file, it went ahead and asked another component, the linker, to go ahead and reconcile the references.
And like Atomizer said, the compiler only works on one file at a time.
Yes.
But also, if you were, just like before, you could undo what Nelson's just done. You could take those 2 functions from input and put them back in, replacing line 5 and 6 of main.
Yeah, I mean, that would still work.
And now everything's back in one file. And then, like before, where we inlined the methods, you end up with one big program, presumably.
Yeah, one executable.
Yeah.
But we didn't tell it to link about those 2 files. We did. We added it to our Solution Explorer, and we gave it the. We set the exclude from build property to no, which happened to have been done automatically for us. When we compile this program, Visual C++ is aware of these files and passes each one to the C++ compiler.
See, I was wondering what happens if you've got you know, I don't know, legacy code in there as well, and you've got different versions of things that you've tried out that aren't actually getting called as part of your program when it finally builds and executes. Does it start out from, it finds main and then go through and find one by one what it needs, and then sort of bubble outwards from, sort of spread outwards from there, or?
I don't think it does that, but I think an optimization compiler would do that. That sounds like an optimization, less of an actual thing that C++ would do all the time.
So just in run-of-the-mill cases, you would end up with a lot of sort of craft in your code.
Compiler linker relationship would be more apparent if we were manually writing make files instead of having the IDE do it for us. Yeah. Maybe, but still.
He goes on to the list of someone who probably doesn't need to be. I didn't understand the question.
So yeah, and we'll whiteboard this in a second here again. But I do want to just quickly point out header files, the existence of header files and what they're used for. If I had one more file, one more CPP file, and it's called, this file has a function called dostuff. So I'm going to call it dostuff.cpp. Dostuff.cpp is going to have int dostuff. And I want dostuff to invoke my getInt function. So I'm going to take my prototype and copy and paste it over to dostuff.cpp. So by copying and pasting this prototype over, I've now made it aware of these two functions. And I can use them in my dostuff function. So I can say, how about just return getInt stuff plus 42. The implementation of the function doesn't matter.
But Nelson, now you've got the same code written in two different places.
Yep. And even furthermore, now I have to go ahead and manually add this dostuffInt to other places that I want to use it at. And now let's imagine that I added another function into my dostuff.cpp file. I would have to add even more prototypes and more prototypes and more prototypes, and I'll have to copy and paste these around, I'll have to copy and paste that around. It'll just get obnoxious. So what did...
Quick sidebar. Could you call something from dostuff inside of input, or would that cause an infinite...
Oh, no, I could.
Problem.
Well, it would cause an infinite loop in this case, but I could do, like, in the getInt method function, I could say if input equals stuff, then just return out or something. Or
okay,
but I could.
Don't go into great detail. I just wondered if that was a worry.
It's possible to do. You can have circular dependencies, but not at the header file level. At the CPP file level, you can.
So what's a header file?
Okay, a header file is a convention in C++, in common C++ programs, where you take all of the prototypes of all of the functions that you want to expose, and you place them in a file that you can include into every other file. Now remember how we talked about the include directive? This is a preprocessor directive, meaning, remember the 3 steps? We have the preprocessor, which executes all the things with the hash in front of it. Then we have the compiler, which compiles CPP files individually. Then we have the linker that takes all the compiled CPP files and mashes them together to get an executable. The preprocessor, the include directive, simply takes the contents of a file and copies and pastes it right where that include statement is. So for example, for all intents and purposes,
nice.
I missed an end if pair.
You failed.
I'm just going to grab the whole thing. And then I'm going to remove the pragma once. Build succeeded. And I can do the same with iostream. I can go ahead and just take all the contents of iostream and I can paste it right into my program. I mean, hey, I can even do the same thing right here. I can take this and dump it right there. That I could just keep on doing this recursively until there's no more include statements.
Which, isn't that essentially what the linker does?
No, this is what the preprocessor does.
Hmm.
The preprocessor literally has taken all of this code that used to be packaged up with nice include statements and has copied and pasted it right above my code. This is literally the same program. As you see, it behaves exactly the same.
So you guys have written thousands and thousands of lines of code already. You just had no idea about it.
Will it result in the same size executable after compile? Yes. The header files, like I said, there is no difference between taking the contents of an included file, copying it, and pasting it right where that include statement is. And I do want to point out that C++ files that use iostream are significantly larger, in the order of thousands of. No, I believe it's in the order of it's like 30K, 40K, or something like that. They're that much bigger just by including an iostream. The actual .exe files are significantly bigger by including an iostream compared to including an stdio.h, which is the input and output code that was used in C.
Okay, you're losing me now.
By using an include statement, the size of your executable goes up.
Because you're basically bringing, well, it's kind of, like I was saying before, you're bringing in a lot of functionality and then not using it.
Well, we are using, well, not using all of it, but we're using
it. Not necessarily everything. It's bringing it, whether or not you're using everything in the string that you're including there, you're still including it.
Yep.
Is there a more efficient way of going about that, or is it just unavoidable?
Well, there is. See, the reason why iostream and string are so big, and I don't want to scare people off, but the reason they're so big is they use templated classes, which can't be separated between H files and CPP files. Normal classes can be separated and should be, but templated classes cannot. So that's why iostream and string are particularly large. Okay. So yes, header files. How can we avoid including everything? There's no way to avoid including everything. You're either going to use the string object or you're not. And it's not the end of the world. It's not that bad. But I just want to point out it is one of the annoying things that people complain about is the size of the standard library. Not in regards to functionality size, but in regards to implementation size and how it blows your executable. Okay.
Show me a header file.
Header files. So what we can do is we can take our prototypes that we'll use and we can place them in one centralized location. Typically, the convention is to create a header file for every CPP file. So I'm going to write a do stuff header, and I'm going to write an input header. So you'll notice I have a dostuff.h and an input.h. I want to point out that the fact that these are in the header files folder is irrelevant. In fact, these folders aren't really folders. They're virtual folders that don't correlate to anything on the hard drive, and they can be in any of them. But you'll really want to separate your .cpp files from .h files because they're very different. So header files allow us to take the code that we would normally have to copy and paste over and over again and place it in a central location. Now notice right off the bat our header file has a problem. Our header file needs to include string. So now every time you include input.h, you have to include string as well. So for the dostuff header file, remember dostuff, the CPP file, only has one method in it, dostuff, or one function in it, dostuff. So I'm just going to copy over that prototype. So now we've taken our prototypes and we've placed them in our header files, which is great. Now in main.cpp, I can include both of these header files right into main.cpp without having to redefine the prototypes. So I can say include input.h and then include dostuff.h.
Could you put your H files on one side and the CPP files on the other, please? Just it hurts my brain otherwise.
Well, anyway, so we have our dostuff and our input header files. And all they do is they define our prototypes. That's it. So now main becomes a lot simpler. We just say include input and include dostuff. That'll literally take the contents of these H files and paste it in there. Now inside of our input.cpp, although we do not need to include input.h, we can. In fact, I'm not going to include input.h here because we don't need to. Although we would typically do it, I just want to stress the fact that there is nothing special about header files. They're not some magical thing that magically links things up for you behind the scenes. They are literally files, text files that contain text that gets literally copied and pasted into wherever you have a preprocessor directive that indicates that the preprocessor should copy and paste that file. Nothing magical about them. So now inside of dostuff, instead of having these two get in prototypes, I can say include input.h. And now I've made the compiler happy.
So why have they got quotation marks then rather than angle brackets?
It has to do with where the preprocessor is going to look for the file. So with the quotation marks, it's going to look relative to where the CPP file is. And with angle brackets, it's going to look in standard library locations. Or externally included locations.
Okay. So it's... Sorry, dumb question.
Okay, how is everybody feeling about header files?
I think you should give them something to do with them.
Does having the include in the header require us to have the include in the input.cpp? Having the include in the header require us to have this include in CPP.
Actually, if you show input.h and input.cpp.
What's going on?
You've got include string twice.
Yes. Which I don't have to. I actually don't have to have this up here. The reason I don't have to have that up here is because currently, and this isn't always going to be true, but currently, input.h just happens to be always included after string.h is included. Remember, .h files are not compiled. Only .cpp files are compiled. .h files are ignored. They're only used when you include them in. So what happens here is that in main.cpp, this include simply turns into this. Copy and paste. Which means for the moment, this .h file will be usable. However, if I decided for some reason to include input.h in another file that didn't include string, or if I happen to include string after I include input.h, then this won't compile anymore. And the reason it won't compile anymore is that there's no longer the coincidence of this H file being included after a string.
Somebody said, if you have it in both, does that double the code at compile time?
That's a good question.
Particularly given that you're doing it with a string, which you said is quite a bloaty thing to start with. You really don't want to have that happening several times.
All right, so we're about another hour in, so I'm going to go ahead and pause and go on break for a minute. We are resuming. Remind me what I was saying before I almost died.
You were saying something like that.
Ew. So,
oh yeah.
Well, no. Let's start with this question here because that will probably push you back into it quite well. Does having the include in the header require us to have the include in input.cpp? Was where we were.
No.
And then
no, it doesn't. If we weren't using a string inside of main.cpp, we could get away with not using the include string here in main.cpp. However, even if we take out string.cpp, it'll still work. Line 12 will still work because input.cpp includes an include to string. Whatever. Just string. So, yeah.
But so how come it doesn't add twice as much cruft?
That's
to your program.
A good question.
When you include it in both places.
That actually leads me to the next question that somebody asked. Could we just do away with input.cpp and dostuff.cpp files and place their contents in a header file? Answer's no. Watch what happens. First of all, note that input.h is included in two CPP files. It's included in dostuff and it's included in main. So if I take the contents of input.cpp and place it inside of input.h, guess what we're going to get? Can anybody guess what's going to happen?
Ooh. I think I can, actually.
We're going to get a nice little linker error. Well, actually, first of all, because these these include. I'm just going to take out the code here, so that they don't use C in or C out and recompile. Now we'll get nice little linker errors. We get a linker error saying that these two functions are being redefined. Remember, the contents of this file are being placed in main.cpp and dostuff.cpp, meaning that the linker, once it gets all the object files, it's going to say, wait a sec, there are two get-ins defined in our program. We can't have that. In addition, there's one more problem with this code. So does everybody understand why we can't just put the contents of the CPP file in the .h file? Because they'll get included into multiple CPP files and we'll get a linker error? Because I'm going to move on to another thing that will finally answer the question about having multiple include strings.
Finally? Yeah, man, you're taking like forever, dude.
Okay, so what happens if we include... Can anybody guess what happens when we include input twice? I want people to realize that we already are including header files twice. We're including string twice. So shouldn't this work? And that was more of a question of can you like parse the inflection of my voice than actually answer the question. But basically the answer is no. We'll get a nice little error. We'll get an error.
Well, surely if it's a question of parsing inflection, the answer is no. We'll get an error. Sorry, continue.
Or in this case, main.cpp, input.cpp. What? Why is it not giving me an error? Give me an error.
Carl. You can't do that, Carl.
See, it gave me an error on Monday. But it's not going to give me an error here for some reason. Well, I'm going to restart, because that really should be an error.
If in doubt, restart Visual Studio.
I'm going to try one more thing, and then we're just going to move on, and I'll explain why there should be an error.
You've really got to find somewhere else to stable those reindeer.
Okay, anyway, this should be an error because we are redefining these prototypes multiple times within a CPP file, which I might have been wrong for some reason on that, which I could have sworn I was right. I'm always right. What is this madness? Okay, so we are getting some proper functionality in this particular case for whatever reason. But the fact is, we are redeclaring or reprototyping out these functions. I mean, really? Let me try something because I think it might have been the extern int that threw the extern that threw the error, or not? Huh? Well,
You kind of lost me, I have to say.
You what?
You've kind of lost me in the minutiae.
Well, Jason, you know what I'm getting at, right?
Actually, Jason's not over on your monitor at the moment.
No. Basically, what I'm saying is that typically, when you define multiple things in .h file, let's say we have a constant. This I know will throw an error. If I include input in twice, this better throw an error. I'm going to be very upset. There we are.
Hooray! It didn't work.
Okay, what we're getting here is that because we're including an input twice, and if I had a class in here, we would get the same thing. Although, ignore this bit, but if I had this class in here, we would also get an error. If I had a type def inside this input.h that got included twice, we would get an error because of the multiple redefinitions of the same thing. So, to combat this, and this leads into why including string multiple times doesn't cause a problem. To combat this, what we do is we include what are called include guards.
Sounds like something you do to a carpet.
An include guard, notice that my project compiles now even though I'm including input twice. An include guard should be used on every .h file that you write. And what it does is it prevents the contents of the .h file from being printed into the same CPP file twice. Now, the contents of this input.h file can be included in multiple CPP files. So I can include this input.h in multiple CPP files and won't get a redefinition error. But because I've included this include guard, if I try to include input twice, I don't get that error. And this becomes really, really important in the case of nested includes. For example, string is nested inside the input.h because we need the std string object in order to make this parameter. So people have already realized that, hey, wait a sec, main.cpp, we're including string twice. Why doesn't that cause a problem? Well, it doesn't cause a problem because of include guards. If we actually open up string, you'll notice it has include guards.
In fact, it has belt and braces.
Does what?
It has belt and braces of include guards. Because not only have you got, if it's defined, you've got pragma once.
Yes. So pragma once is a preprocessor declaration that only works in Visual C++. And pragma once is basically the equivalent of an include guard, but I recommend not using it and avoiding it because it makes your code less portable between compilers.
So that's a Microsoft thing, is it?
Yes. So because we've now included include guards, we can now safely know that these things aren't going to be redefined. Does that make sense?
Yeah.
I'm terribly...
Because, I mean, it even reads, they even read exactly, I mean, it's the same thing you would do in code if you wanted to make sure that you were adding something to a list. You would do, if the list already contains it, don't add it.
Right.
And here we're saying, if this is already defined, don't define it again.
Yep. We're saying if not, that's the N, def, or defined, do stuff underscore h, then define do stuff underscore h, and then this is the end of the if. Now these are preprocessor preprocessor declarations, so they only happen during the preprocessor step.
Is there... I don't know quite how to phrase this. Why is an end if required other than because it's required syntactically? Why is it syntactically required?
Because
do you see what I'm asking?
You can use if defs and if end defs anywhere you want. They're not just used for declarations or for include codes.
Oh, okay.
We can say something like, if def win32, else end if, and then here we could write some code. Then here we can write some code.
Okay. I just wondered because presumably every H file would have to be in a separate, H file.
Right.
Yes?
Well, yeah.
Hello?
Hello?
The functionality of an H file, does each one has to be in a physically separate file? In the same way you can have more than one class in a CS file.
Mm-hmm.
Is that not possible with H files? Am I not asking this clearly?
You can. I can have as many things as I want in this. In fact, I could delete the input.h include file and copy and paste this over to the dostuff.h. And that'd be fine. If dostuff.h has not been included, define dostuff. Yes. Well, no. More specifically, if dostuff.h or dostuff underscore h has not been defined, then define it. So we're basically setting a flag. We're saying, okay, if this has not already been defined, then define it. Then this is the end of the if statement. Now remember, this is all preprocessor stuff. This has nothing to do with compilation. All of the preprocessor declarations are figured out prior to compilation, the beginning of compilation. And the define flag is for each CPP file. Yes. The define only matters for a particular CPP file. It doesn't transcend CPP files. Remember, the unit of compilation in C++ is a CPP file. .h files are not compiled, and they only ever do stuff if they're included into a CPP file. So does anybody have any questions about headers and CPP files? Because I'm about to jump over into the whiteboard and talk a little bit about the linkers some more.
Yay!
I know we've been saying the word linker, preprocessor, and all that stuff, and I want to go ahead and make it, now that we've talked about it for a little bit, actually show people a visual representation of what it does. Any more questions before I jump out of code?
No, they've either died or they want to see you on the whiteboard, one or the other.
And probably so they can laugh.
Hey, you're getting better.
Okay, let me find my tablet. Okay.
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 Okay. Okay. So what we have is three steps. We have the preprocessor. No idea if that's how you spell it. The compiler and the linker. The preprocessor and the compiler get CPP files. So CPP files go into the preprocessor and then into the compiler individually. Then they all get compiled into OBJ files. So each CPP file goes into the preprocessor, which handles everything that starts with a pound. So the preprocessor handles includes, for example. Then, no, I'm not answering what sin.ignore does. Then, after the CPP file gets done with the preprocessor, it goes into the compiler. The compiler spits out OBJ files. The linker gets these OBJ files and spits out an executable. That's not even close to an X.
Well, VWX, it's not that far apart.
Okay, so CPP1, CPP2, and CPP3 get turned into OBJ1, OBJ2, and OBJ3. They get linked, smushed together into an executable. So, for example, if we have a dostuff.cpp, that has an int dostuff method, that does stuff. What it does is irrelevant. Then we have a main.cpp that has a prototype for int dostuff. Then an int main. That invokes dostuff. And then returns 0. I'm not even. I killed the D. So it does more stuff, and then it returns. Okay. When dostuff gets compiled, so when dostuff.cpp gets compiled into an OBJ file, what is in the OBJ file is simply the implementation of dostuff. This is going to be the assembly of the dostuff function, the compiled assembly code for dostuff. Now, when main gets turned into an OBJ file, what happens is dostuff becomes a placeholder. The compiler does not know how to dispatch a compilation or dispatch an invocation to the dostuff function. So this becomes a placeholder. And it's important. The prototype is so important because the prototype actually gives the compiler specific information about what the placeholder represents. It says this placeholder represents a function called dostuff that takes in no parameters and that returns an integer. Using that information, the compiler is able to create a placeholder function invocation of dostuff when it gets turned into an OBJ file. So we have the main function, and then we have the dostuff placeholder. Is what's in this OBJ file. Now the linker gets access to both of these files. Remember, these files from the compiler onwards are completely independent of each other. There's absolutely no relationship between these two CPP files. They get pre-processed and compiled in isolation entirely. So when they get turned into...
placeholder is just like a socket that the linker plugs do stuff into.
Yep. So when we link these, the linker is going to take this, plug it into this placeholder, and then it's going to spit out an EXE. And the EXE is going to contain the object code from this file and the object code from this file. It's going to be linked and it's going to be spat out as a program.
Hurrah!
Okay. And the solution handles all the logic for which objects the linker should smush together. Yes. The solution file, when Visual C++ goes to compile this, what it actually passes into the compiler is this, if I'm not mistaken, it's going to be this VX or VCXproj, which contains, which tells the compiler. I can just verify this really quickly, because that's how. Well, either way, the solution when building from inside Visual Studio informs the compiler of all of our CPP files. So if we look inside this debug folder, you'll notice some cool stuff. Hey, look, those are our OBJ files. These contain the object code, and then they get linked into the executable. And they get linked, they get associated with, because Visual C++ informs the compiler about all of our CPP files.
So why is there so much other stuff in there as well?
That's just temporary garbage. Last build state, an embed manifest, and a bunch of other fun stuff. What do the OBJ files look like when you open them? They're just binary files, so they're not going to look like a whole lot. You'll notice, though, that they declare, you'll notice some strings in here that are readable to an extent. So here's all of our STD stuff. In fact, we can find the do stuff. Yeah, here's, I believe this is the list of functions that this OBJ file contains, and here's a reference to our do stuff in plain text. But the most of this is just object binary data.
Oh, there's lots of fun-looking stuff in there. Anyway, that's going a bit beyond. If we go any deeper in there, that's going a bit beyond where we are. So are there any more questions on how your CPP files end up turning into a runnable EXE?
I do want to point how much I would have loved for somebody to actually teach me this before using header files, because I spent so long looking at header files and be like, how this doesn't make any sense, and then not being able to debug header files or the relationship between CPP files is going to cause you lots of misery. So I really want to make sure that people understand this. So who's having issues with this?
It seems like another one of these cases where there's a lot of scary words and acronyms and things involved, but the actual process, if you can get past all the terminology, is quite straightforward and sensible. Conceptual
issue. Header file equals template in a sense. I might see where you're going with that. I would avoid using the word template, though, because that has a different meaning in C++.
Blueprint?
It's
List of requirements?
It's a forward declaration. That's the best thing I think that's the most technically accurate way to say it. It's a forward declaration. You're declaring that something exists somewhere. And where that something exists is irrelevant, other than the fact that it does exist. So you'll see that something, this doStuff function, exists somewhere. Now, we don't know where, but it exists somewhere. And then in main.cpp, we include our doStuff header so that we can invoke this function. But it's not actually linked up until the final stage of compilation. Is that all header files are used for then? Header files are used for forward declarations. They're used to declare constant values. They're used to define, or not define, but declare classes and structures. They're used to declare type definitions, or type defs, which we are not going into. I mean, type defs are actually just really straightforward. Actually, I mean, honestly, I can show you what a type def is right now. Basically, I've just created an alias for the int type to be thing. So every time you use thing now, it's an int. It's kind of like a define, but it's limited in a good way, in that you can't do stupid things with it. So that's what a type def is. That sort of stuff goes in H files, so that they're accessible. Yeah, it's an outline.
Cool.
So yeah, is that it? Are we moving on from the linker? I always feel like the Friday class is half asleep.
It's that Friday feeling. I think it's because you have to second guess yourself all the time, because it feels like, hang on, did I just say this? Oh no, that was Monday's class. Well, that's what it feels. I'm like, did we cover this in Monday? Or was that a different week or a different class?
Okay, because you guys know that the last thing that we're going over is just namespaces, then everybody goes away.
Well, homework.
Well, yeah, then homework. Like, come on, so we have plenty of time for questions if people have them.
I don't think anyone has any questions. If they do, they're keeping quiet about it.
I'm a bit confused about how you manage all the includes between different CPP files and how it seems like they can get hairy. Yes, CPP files and H files and managing the relationship between them it's not something that's easy to do, and it gets very confusing very quickly. But I'm going to give you a few principles to always follow in regards to CPP and .h files that will make it consistently less difficult to conceptualize. First of all, always, always, always use include guards. Second of all, you should always have a H file that corresponds with the CPP file if the CPP file has functionality that you want to be accessed at a different part of your program. So a CPP file should always relate to a .h file. Or actually, more specifically, a .h file should always relate to a CPP file. You might not have a main.h because there's not much reason to have one.
No, well that makes sense. If the main's the only thing in there, it's doing all the calling. It's the one in charge.
Can I use type def in homework? That's up to Gav.
No.
No. I was just showing that just as an example of what would go in an H file.
Sorry, but no, it would just get too confusing.
Main needs to include all H files? No. Main just needs to include the H files that are relevant to it. See, for example, main might include input.h, which might forward declare getInt, But here's the thing. GetInt could potentially invoke code that's in another header file that main doesn't know about. What input.cpp includes is none of main's business. All right, let's talk about namespaces, because namespaces are very straightforward.
Right.
Well, they are a straightforward thing to know about and to learn and to see, but they're not necessarily a straightforward thing to apply. But still.
Ooh. So what? Line 3 of input.
Right, and actually I'm going to pull up main because everybody's used to seeing this in main. So you'll notice on line 7 we say using namespace std. And what that does is that imports everything in the std namespace into the global namespace for the use in this file. So what's going on here is everything in the std namespace is made accessible to main.cpp. So iostream and string both define things in the std namespace. And the only way for us to be able to access it is to either prefix every reference to any of the things in these headers, such as string and cout and cin, with std : or to explicitly import each type, or to blanketly import every type and object. So as everybody should be familiar with this by now.
So there's kind of pros and cons to using namespaces then?
Well, they're used to avoid name collisions. And that's really important. Like in certain languages, it's common for every single program you write to be wrapped in a specific namespace, which means you don't have to worry about name collisions as often. That's less likely in C++. There's a much greater likelihood of name collisions.
I was thinking also in terms of just, you touched on there again, the bloat from using a namespace.
No, that's...
or does it not?
That's the bloat from the include. Whether or not we import anything is irrelevant.
Okay.
So everybody should be familiar with importing std by now. And if you're not, what I'm about to show you will be very confusing. So is everybody familiar with importing std?
Cool.
Okay, let's make our own namespace. In my dostuff.h file, I'm going to make a namespace. I'm going to call it namespace njl. And that's how you put something in a namespace. I mean, yeah. Again, syntax isn't very difficult. The keyword namespace, the namespace identifier, an open curly, the stuff you want inside the namespace, and then a close curly.
And there's no potential for accessibility modifiers or anything like that?
No. So now if I go ahead and do a Control-Shift-Build, you'll notice I get a few errors. First of all, in main.cpp, I get a compiler error because dostuff.h is now wrapping the dostuff function inside of the njl namespace, which means I'll either have to do this, njl : or using namespace njl. Is everybody good with that?
Yeah, because dostuff is no longer just dostuff. It is njl.dostuff.
Mm-hmm.
It's become a differently named or differently referred to thing.
Any questions about why I need using namespace njl right here? Are we all good? Yeah, everyone good? What namespace was do stuff in before NJL? It was in the global namespace. It basically wasn't in a namespace. You call it the global namespace. That's, I guess, what you could call it. It was in the global namespace.
Is that essentially just your program?
It's the root namespace. So could you effectively have two completely different do stuff functions that are managed by different namespaces? Yep. And that's the biggest awesome thing about namespaces. So I can now have a namespace blah with a do stuff method inside of it. And that won't cause any problem. Nor will it cause any confusion inside of main. Because you'll notice, I did get an error, but that was actually the error that I was going to ask a question about to you guys. But we don't get a compiler error because main knows which do stuff we're talking about because we imported NJL. If we imported both NJL and blah, we'll get a nice little compiler error because it doesn't know which one to use because we've imported both namespaces that both have an int do stuff. So we would need to qualify which one we want.
And A-Shield said, do you at this point have to declare the namespace before the function?
Yeah.
Wow, I did a whole time lapse thing there. Sorry, carry on.
Okay, if I hit Control-Shift-B right now, what is going to happen? Any guesses? And be as specific as you can. Oh, Control-Shift-B, that's funny. That builds the program. It compiles it.
I just love that, yeah. But particularly for anyone who's not using Visual Studio as well. It's probably just go, I don't know.
F5 starts the program with debugging. In Visual Studio, Control-Shift-B just rebuilds it.
Like F6. Although I suppose does it not save it?
F6 does save it, but F6 only builds the current project you're on, whereas Control-Shift-B rebuilds the entire solution.
I just assumed one was IntelliSense, one was ReSharper. I didn't realize.
They do have different uses, especially when you're working projects with a bunch of, or solutions with a bunch of projects. Okay, people are actually answering correctly. We get a nice little linker error. You get a linker error saying NJL do stuff isn't defined. And then you'd be like, well, I put it in the CPP file. And then you'll look at the CPP file and you'll realize, well, wait a sec. This do stuff is not this do stuff. They're completely different functions. This is encased and qualified by namespace. This is not. As a result, they are two different functions. So all I have to do is simply say namespace NJL. And now if I do Control-Shift-B, we get a valid compilation. Any questions thus far about namespaces? Again, very simple, straightforward stuff. I'm going to go ahead and have put input in my NJL namespace as well.
Doesn't seem to be any, no one's shouting out with questions.
Everybody's asleep, I guess. I guess I just put Friday people to sleep. Okay. Sweet. So nobody has any questions about namespaces. Let's talk really quickly about the anonymous namespace. Is everybody ready to talk about the anonymous namespace?
I'm just hugely eager to do so.
Yeah.
What's it called?
It's actually called nothing. Okay. I'm going to architect a problem in our code.
No change there. Sorry.
Okay, what I've just done is I've created two helper functions that the intention is that these helper functions are only used by the other functions inside of these specific CPP files. They're not to be exported, and they have no meaning outside of these CPP files, and I don't want anybody else to use it. Most importantly, I don't want it to conflict with any existing definitions. So just to see if you guys are all still awake, when I hit Control-Shift-B, what's going to happen? It'll build my solution. It'll try to build my solution, but Mr. Linker is going to say, hey, you have two functions named helper function. That's a redefinition.
Naughty, naughty.
So how do we fix this? There are two ways. We can use the static keyword. The static keyword is leftover cruft from the C programming language. This does not mean what you think it means if you are familiar with C#. C++ does have staticness like C# staticness, but this is the static keyword being used in a different context. What the static keyword does is it means that this function is not going to conflict or be accessible by any CPP file outside of the one it's defined in. But, of course, C++, we're like, well, we want to use the static keyword in a different connotation, and so we want to get rid of this and write a cleaner way to express the same logic. So in C++, we have the anonymous namespace. The anonymous namespace, all this does is it makes it so that the functions inside of this CPP file, or specifically the functions defined within the anonymous namespace, do not conflict with anybody else. That's all it does.
So it's actually more equivalent to something like private in C#.
Yeah, it's similar to that, but in the context of namespaces, or the context of CPP files. So what we've done is we've said we're going to define a helper function, but it's not going to conflict with any other function named helper function, and other people can't access it from outside of the CPP file. Everybody good with anonymous namespaces? Do anonymous namespaces need to be nested? No, they do not. They can exist outside of the namespace if I wanted to.
Would that mean that it's only available in global then?
I can still access it from within here.
I mean, is there any point to... Well, I can't immediately see why you would want to do that outside of any namespaces.
It doesn't matter.
Lot stops any of the namespaces that aren't just the global from using it.
It doesn't matter. It really doesn't matter. There's no difference, really. No significant difference that's going to impact anything.
Oh, it locked... Okay.
But I just wanted to answer the question, no, they don't need to be nested. So it can only be used in that file, yes. This function can only be accessed within this one file. So anonymous namespaces are local to each CPP file, yes.
But what if you had more than one namespace inside the CPP file? So you had an NJL and you had some stuff in there in a
No, you mean like
namespace
blah, and then I had a function called void, hey, and how would I get to helper function?
Well, more to the point, how would your anonymous namespace, if it wasn't inside one or the other, know which one it applied to? Or would it apply to both of them?
Oh, it doesn't matter. It applies to just this file.
So it would apply to both of those?
Yeah. I would be able to access helper function from either of these.
Cool.
So because helper function didn't have parameters, it's not overloaded. Well, yeah. If if this helper function took in an int I and this helper function took in a float f, that makes these two functions completely different, and that would not cause a linker error, even if they were outside of the anonymous namespace. But that's irrelevant. Why should you use the anonymous namespace, not the static keyword? Because anonymous namespace looks better, and you don't have to repeatedly type in the word static. And static has a different meaning elsewhere in the language specification that might get confusing to other people. Anonymous namespaces are C++'s version of the static keyword used in that context. So what does static mean in this context? In this context, in a function, static just does exactly what this anonymous namespace does. If I added the static modifier to a function, it would do the exact same thing as the anonymous namespace. If you have a static member on a class, that has a different meaning, completely different meaning.
Did you mean to have line 9 of input be static still? Or is that might be what's confusing?
Yeah, I didn't mean to have it there. Sorry.
Okay. Well, there's no questions coming in, but...
and honestly, that's about it. There's one more thing.
Is that about...
What?
No, I was about to say, is that about it?
Actually, there's one more thing that we need to talk about, and that's global variables and how to access them across CPP and H files. One more time, why have anonymous namespaces? If I did not have an anonymous namespace here, or here, and this was an NJL, without having anonymous namespaces, these two helper functions, which I just named helper function because often random miscellaneous helper functions you might write will have similar names. However, I don't want these helper functions to be used anywhere outside these CPP files. And most importantly, I don't want somebody who uses a helper function in another CPP file that happens to be the same name. I don't want that to cause my program not to compile. As you'll see right here, we get a nice little linker error because these two helper functions are conflicting because they have the same signature. By placing them in the anonymous namespace, it localizes them to the one file and avoids any linker ambiguity. So even after the linker joins everything together, the anonymous namespace keeps the functions to themselves, to their one CPP file. Yes?
We do have a question that came in. For readability, would it be better to name your namespace the same as the CPP file that it's in?
No. Namespaces should be, generally speaking, for very small projects, if I use a namespace, it will be the name of the project. In fact, I would typically recommend people to do so. But that name of the project would be global to every CPP file. Now, if you run into a situation where you have a large component or subsystem of your project that you want to sort of...
UI?
Do what?
Oh, sorry, I thought you were trying to come up with an example. So like UI section that dealt with that, or...
And you wanted to segregate them logically. Then you'd introduce an additional namespace. Okay, let's talk about global variables, and then we're about done. Okay, so global variables. Very interesting stuff.
Variables you can access globally. The end. Is that it?
Nice. What? Yeah, I know I had that in there before and it wasn't. Oh, yeah, multiple words. Derp. Okay. Global variables are variables you can access between functions. Typically, they are bad and should be avoided and are horrible, horrible, horrible things that will destroy your program, slowly rot away your code base, and result in you quitting your job because you're absolutely sick at looking at such a huge mangled code base of death.
And you will be required to use them in this week's homework.
Unfortunately.
Couldn't resist tagging that there. Explain.
Basically, in this week's homework, we're going to be working with an array of strings. However, passing arrays to functions are non-obvious, painful, and would require another lecture about pointers specifically to actually talk about and have people understand.
And of course, we'd love to sit here for another 2 hours and talk about pointers.
Yeah.
And then like carry on and maybe have brunch and talk about all the good things we can do. But, we don't want to keep you here too long.
And NATO, it's not that I'm biased, it's that almost every single programmer in the world is biased against global functions, or global variables, sorry.
Shinja's discovered my secret plan. He said, so the homework challenges are meant to erode the soul slowly.
So the what?
Never mind. Why are globals bad?
I really don't want to get in. I mean, they're just bad. We'll talk about more why they're bad once we have a way to avoid them.
Okay.
But they're difficult to reason about. They're difficult to, once your program grows in complexity and size, they're difficult to know how they get edited. So yeah. Yeah, it sort of defeats the purpose of OOP. But that's what once we start talking about pointers and OOP, then the need for globals will all but disappear. Okay. Global variables, that's it for them really, but there are some considerations. Let's talk about how global variables interact with the linker. Let's say I have a string name in main.cpp, and then I had a string name in input.cpp. Can anybody guess what's going to happen when I hit Control-Shift-P? I get some linker errors. Name has already been defined. So how can we fix this? Well, we can, of course, stick it in an anonymous namespace. That would fix it, which is typically what you would want to do. But what if we wanted to share a global variable? Let's jump into a header file and do it. Let's jump into our input header file. Let's say we wanted to share a global variable between everybody. We can't do this. If we do this, then the contents of the header file are going to be printed into every CPP file that it gets included in, which will result in the exact same linker error that we just saw. What we need is a way to prototype a global variable. Unfortunately, in C++, there is a way to do so. The extern keyword makes a global variable, it turns a global variable into a global variable prototype. Simple enough?
So would you leave it where it is then?
Yeah, I would leave it in input.cpp. Or I would define it in input.cpp. And then I could use it from main. Include guards would prevent the linker error. No, include guards only prevent the .h file from being included in multiple CPP files. Input.h can be included into up to one time in every CPP file in your project. So I can include input.h in main.cpp, in input.cpp, and in dostuff.cpp. All the include guards do is they prevent it from being included twice within the same CPP file. Does a global variable need to be in a namespace? No, it doesn't, but I would advise that you do so. Because? Because typically when I have free-floating functions like this and free-floating local variables, I really like scoping them in the context of namespaces because of name collisions, and it looks nicer, and yeah, there's no reason not to. And you want to avoid name collisions, and you really want to package up your code in packages. I mean, hey, namespaces are called packages in certain languages, even.
I always think a rule of thumb is you should always name everything and place everything, decide where to place everything based on the idea that you're writing it for somebody else to use.
Yeah.
You should make things, things should be named explicitly so you can see what they do. And in the same way, if something is specifically for use in, like this product name is for use in the NJL namespaces, whatever it does with it, then you should put it there and keep it there.
Right.
Kind of an extension of make everything as private as possible.
Yeah, and it's a conceptual thing. It's an intuitive thing. It's a design thing, and it's an important thing, really. But doesn't global mean it's outside of a namespace? No. When I say global variable, I mean a variable that is not encapsulated in either a class or a function. Although this variable is being nested inside of a namespace, that doesn't mean it's not global. It still is a global variable. Does a global var need to be in a namespace? No. We could have a global variable outside of a namespace if we wish.
Couldn't you just have like a globals.cpp?
Nah. You could, but I'm going to be showing a better way to do it. And give a hint about the homework.
Cool. That was a very restrained response. I expected more.
We'll talk about it. We still have to talk about the extern keyword.
Talk about it.
Okay, so let's say in
external
main.cpp, I say product name equals whoa, cout product name. And I can do this because I'm importing the NJL namespace, and product name is defined in this input.h file. But when I hit Control-Shift-B, I'm going to get a nice little linker error. It's going to say unresolved external symbol, and it's going to point right at my product name. So what's going on here? Remember, the extern variable is exactly like a function prototype. We're promising the compiler it exists somewhere, but we need to define it somewhere first. Or not first, at some point, so that the linker knows how to link it up properly. So how do we do that? Well, I'm going to jump into input.cpp, and I'm going to say string product name. By doing this without the extern keyword, I am providing an implementation for this external variable. And as a result, program compiles.
See, this is where, for me, it gets conceptually, it rubs up against the whole idea of interfaces and abstract classes and such like.
Right, but see, with the C# class, we could jump almost like, after
yeah,
6
I
week
don't want
course
to lead
into
people
design.
astray,
But here, there's a lot of stuff to take into account. But its scope is only limited to whatever CPP file this header is included in. but its scope is only limited to whatever CPP file this header is included in. Not necessarily. You can think of it like that. That's a valid way to think about it. But I could have just as easily done, and just like how I can take these function prototypes and put them directly inside of main.cpp, I can also take this extern variable definition and place it directly inside of CPP. Remember that the include simply copies and pastes the code. So basically, I don't have to include input.h. I could have just copied and pasted in here, but I would prefer to, because it makes things more centralized and clean. Why do we have to declare extern in the H and not the CPP? Well, the reason is the extern is really only specifying that we're providing a prototype for a variable, just like how we prototyped our functions. And the extern keyword was born out of the fact that a function prototype is easy to differentiate because it doesn't have a body. Because getInt has no body, the compiler can look at this and say, well, he obviously is talking about a function prototype. However, without the existence of the extern keyword, the compiler would look at this and say, well, this looks just like a local a variable definition. There's nothing saying that it's a prototype and not a variable definition. But here we are doing a variable definition.
See, this is the thing. This is why the extern is saying you have to define.
Right.
This at some point. And the one on the left is actually doing that.
Is it okay to use global constants? Yeah. Constants are fine to be global. The problem with global variables is that they change, and it's difficult to conceptualize, or it's difficult to reason about a global variable because you won't immediately know which code is responsible for changing it because it can be changed by everybody. But a constant solves that problem because, well, per definition, it's not going to change.
And also, if you think about it, if everybody has access to this variable, anybody could change it.
Yep.
And you don't, even in quite brief programs like this, you've still got the potential for confusion as to, well, why is that variable being set to that value at this point in time?
Yep. And code written like this, if it's of any substantial size, let's say more than 1,000 lines long, you will get confused by reading through code that makes heavy use of globals.
And NATO, yeah, that's absolutely right. It can't be changed because, well, it's a constant.
Yep.
It's our constant.
Okay. Any more questions about global variables and then in the context of header files?
Could you just give a brief summary of what goes in CPP files and what goes in H files? Just because obviously there's been a lot of information spread across this video.
Right. CPP files have your implementation. So it has the code that you write that needs to do stuff. H files contain prototypes that provide or that make your code aware of the existence of other code without knowing how exactly it's defined. So if I jump back into here, H files make your code aware of what's available elsewhere, but don't necessarily define it. CPP files fulfill that contract. Okay. So one last thing about global variables is a less bad use of them would be in the context of an anonymous namespace. So for example, if I took out this product name and I instead placed it into this anonymous namespace, now I've encapsulated this data so it's only accessible from within functions defined in input.cpp. So it gives us some level of control.
Atomizer asked something, but I kind of got lost halfway through the second line.
What?
Doesn't it? What about defining the same global variable in the CPP without the extern that does not include the header file with the extern prototype while it's defined in... Yeah, can you...
Where is this? Erase blind?
BuzzNet. 423 in BuzzNet.
I don't see it there. Hasn't reached me yet. Or maybe I just died. Someone should type something into BuzzNet, or I'll try to. Yeah.
I've just pasted what is at the end of BuzzNet.
What about defining the same global variable in a CPP file without the extern that does not include the header file with the extern prototype while it's defined in another CPP file? Would it link to the prototype global? Oh, good question. So for example...
Can you explain the question first, please?
Yeah, he's asking if I have... I'm just going to pull up another Visual C++.
And I'm not having a go at you, Adam, it's getting a bit late for me now.
Well, his question was, if we had, let's say, a source file that had called ble, and then a... what did I just click? I don't know what I just clicked. And a header file called ble, and the header file had an extern int my variable. And his question was, if I defined a variable in ble.cpp without including the header file, would references to this extern still link up with this? And the answer is yes. So if I created a main.cpp that included in ble.h, and I have an int main, and I say my variable equals 10, cout my variable, it compiles and links. So because remember, header files are absolutely meaningless. They don't mean anything. And this still links up with this variable, even though I don't include in the ble.cpp.
I think we must be fairly close to wrapping this whole thing up.
Yes.
Because they're dropping like flies.
Would anonymous namespaces be equivalent to a static string product name? Yes. So why does taking the extern cause an error? Taking away the extern means that now main.cpp, because main.cpp includes ble.h, main.cpp is going to be redefining our my variable. So if I do a build, you'll notice I get a link error that says int my variable already defined in ble.obj. So because if I take the extern out, then this is going into main.cpp, which is conflicting with the definition on ble.cpp. Does that make sense?
There was one final question from Michael. Would anonymous namespace be equivalent to a static string product name?
Yes, I answered that.
Oh, sorry.
Okay, just one more example. I'm going to remove this header file and show you guys what this code would look like once the preprocessor gets done with including in ble.
So you're going to be the preprocessor?
Yes, at least for this one include statement. I'm going to grab this, I'm going to yank it out, I'm going to paste it in, and then I'm going to delete ble.h entirely. We still get a linker error. We get a linker error because we have two definitions of my variable.
And then all of a sudden the reason why it's called extern makes perfect sense if you put it back in.
Yeah, and if I add extern here, then we're saying my variable is defined somewhere. Go ahead and have the linker link it up for me. And as a result, you'll see that this works.
It's declared externally. In all seriousness, that was like a light bulb just went on then. Because until you actually copied and pasted it in there, I was just like, extern. I just wondered, I thought they kind of picked the word out of the air because they needed one.
No, yeah, that's externally is a good way to think about it. So it's initialized in bled.cpp, but it's declared in main. Yes. I mean, that is correct, but I would say it's forward declared in main, which is a little bit of a more appropriate term, because we're saying we're forward declaring it. We're saying it exists somewhere, but we just haven't defined it. Okay, so is it homework time?
Yay, homework.
All right, you guys see what I did? That's how you get to the homework. Goodbye. Yeah, this is what we're doing. It's the functionality.
Did you see the little clause I added in?
Do what?
Did you see the little clause I added in?
Clause? Where?
Oh, you'll get to it.
Submit a modified version of last week's vending machine. The functionality of the program should remain the same. However, the code needs to be refactored into individual CPP files, header files, and functions as demonstrated in class. No functions, including main, may be more than 40 lines of code when formatted normally. Formatted normally.
Yes. There's going to be someone otherwise.
And 40 lines is ridiculously generous. I just want to point that out. Really, no function should be more than 25. Well, when I say no function should be more than 25 lines, I'm saying 99% of your function shouldn't be more than 25 lines. Any questions about? Oh, we did have one more programming question. The answer is if I had a third CPP file. I wonder if anyone's going to get that. If I have a third CPP file, would I have to declare it again? If I wanted to use my variable inside of this CPP file, so for example, I have a function called hey there, or without the exclamation point, and I wanted to use my variable, I would have to re-forward declare it. I would have to say extern int my variable. Now I can access it. Okay, so homework.
Should be fairly self-explanatory.
I'm happy that someone got it.
Any homework questions at all? Otherwise, we will have to stop.
Yeah.
And nobody wants that.
I mean, well, it'll be over. There won't.
It'll be the end. No, like house. It's nearly finished.
Okay, so I guess I'm just going to go ahead and hit stop. And we just made it under 3 hours of recorded time. So not that bad.
Nice. No, not at all.
So I'm going to go ahead and hit stop. So everybody, goodbye everybody who is listening to the recorded video.
Bye.